Okay, so let us move forward, and our next goal would be to study quotients of Lie group by Lie subgroups, also known as homogeneous spaces. All right, so again, so suppose that we have Lie group, and you have H inside G. It is a Lie subgroup. And of course, you can consider then a quotient of G by H just as a set now, right? So this is so these are all classes, right? Like this. Yes, G goes over G, and sometimes we'll just denote this as class with representative G. So this is some notation, and there is a natural action of G on this. So far we don't have smooth manifold structure here, so this is just action as a Lie group. And so therefore, and so what is our goal? Our goal is to, first of all, let us describe this action first. So I act G, I act on class with representative G prime as follows. It's just a class with representative G prime. So this is natural action, of course. And goal for today, one of the goals is to construct, or define smooth structure on G quotient by H such that this action alpha is a Lie group action. Okay, so we would like to see that we would like to define structure of smooth manifold here such that this action is smooth. Okay. So first about topology, right? So we need to take some topology in here, and let's take a quotient topology. So topology on G over H is quotient topology. That is, U inside here is open if and only if, the corresponding lift of U, P inverse of U, is open. Here, P is a projection from G to G over H. Right. And with this topology, we at least would like to see that it has necessary properties, this topological space, to be manifold. So manifold as the topological space should be Hausdorff a second countable. So let us prove. So Lemma G over H is Hausdorff and second countable. It means that it has a countable base. Right, so let's prove it. Let's prove that it is Hausdorff. So let's take Hausdorff means what? I take two different points and then can find neighborhood of these points open such that this neighborhood does not intersect. Right, so let me fix 2 points, G1, G2, inside G of H, some arbitrary points, and they are different. So the class of G1 does not coincide with the class of G2. So consider this. Right. So since the class of these two classes do not coincide, we have that G1 inverse G2 is not in H, because otherwise these two classes would be the same, not in H. It's important. Moreover, we proved in the last lecture that H as a Li subgroup is closed. We proved that if a Li subgroup is closed, so H is closed. It means that G minus H is open, and this lives in G, so this element lives in G minus H. So therefore, it's open, therefore there is some neighborhood in G minus H of this point, right? So there exists U in G, right, open, and G1 inverse G2 is inside, such that it is actually in G minus H. So U does not intersect with H. Okay. So now let me consider this map phi. So this is map G times G to G, and this takes two elements, and I would like to invert the first one and multiply by the second one. So this is should compare with this. So I would like something like something what's written here. So what would I like from this map? Actually, so let me take a couple of neighborhoods. So let U1 and U2 be, so let this be neighborhoods of G1 and G2 respectively. So let me actually take U1 times U2, which is an open, so U1 and U2, of course, I would like them to be open. So this is open in here, right? And this is neighborhood of G1 times G2. And let me take this and intersect with phi inverse. Of course, these are some technicalities, but we cannot avoid all the technicalities. So let me intersect it with this. All right. So this is actually two open subsets u1 tilde times u2 tilde. Right? So and I have actually right. So my u is this one, right? And g1 comma g2, right, is in the preimage for inverse of u, right? So therefore g1 comma g2 is inside u1 tilde times u2 tilde, right? So g1 g2 is inside here. And moreover, if I map it back by phi, so meaning that phi of u1 tilde times u2 tilde, it is u1 tilde inverse u2 tilde. But this is inside u because I intersected it with preimage of u, so this is inside u. But u is not, intersection of u with h is empty, so therefore this intersection of this, right? So intersection, so this inside u, so intersection of u1 tilde inverse u2 tilde with h is empty. But I can rewrite this as follows. It means that u1, so this implies the following: u1 tilde h and u2 tilde h do not intersect. Indeed, why this implies this? So if on the contrary there exists some u1 in u1 tilde, h1 in h, and u2 in u2 tilde, h2 also in h, such that, well, u1 h1 equals u2 h2, then what can I say? I can rewrite it and express h1 is u1 inverse u2 h2, right? And this belongs to so h1, so this belongs to what? This to intersection u1 tilde inverse and u2 tilde and h. So it belongs to h on one hand. On the other hand, so this is because of this right hand side, it is in here, right? In u1 inverse tilde u2, right? So therefore, but this is contradiction, so therefore we cannot have anything like this. Sorry, then not this. So I have actually can move h2 to the right. I have h1, h2 inverse is in here, side here. But this contradiction, we cannot. So on one hand it is in here because it's u1 inverse u2. On the other hand, it's inside h, of course, because it's an element of h. But this contradiction. And so, therefore, the, 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 there's no such U1, U2, U1, and U2, right? And therefore, intersection is empty. So all this is about this application. Now, on the other hand, this map P that I introduced there is just quotient, right? It's just xg and gives me a class with representative g. So the projection. This map is open, means that it takes open subsets and image of open sets are open. Why is this is true? Because, well, take some open U, right? Well, not this U, but something else, maybe V, right? And then we would like to see that if this V is open, then P of V is also open. But P inverse of V is just V times H. And this is open, this is just union of VH as H runs over H. The union of open sets, so it's open. So pre-image of P of V is open, so therefore P of V is open by definition of quotient topology. So this map is open, therefore I can take P of U1 tilde, right, and P of U2 tilde. So these are open because U1 tilde and U2 tilde are open, and moreover they do not intersect because P of U1 is exactly well, sorry, I should take so U1 and U2, yes, so U1 and U2 they were in G1, G2, right. So therefore P of U1 is in G over quotient by H, and P of U2 tilde is in G quotient by H, and G1 is in here, G2 is in here, and I argue that they do not intersect. So P of U1 tilde does not intersect with PU2 tilde. This is because of this, right? Let's call it again star. We don't have any formulas named by star, so let it be star. And that's it. So we take two arbitrary points and found two open neighborhoods of these points which do not intersect. So therefore this is Hausdorff. Okay, second countability, I will not, so let me leave it as an exercise. So second countable it's exercise using openness of map P. Of P, which we showed. So, all right. Okay, so at least topology wise, we are good. So G of H is has needed topology for being a smooth manifold. Now we need to introduce atlas on G over H. So how do we do this? So let us consider a chart around identity in G. So consider phi. So chart is what? It's a homomorphism from an open set. So I would like this set to contain E, so E in G. To Kn, where n is dimension of G. So this is chart of G. G is manifold, so therefore we can find it. And we also would like it to be what's called centered, right? So such that, first of all, phi of E is 0, so identity E and G corresponds to 0, right? And second of all, this chart is the one from the definition of submanifold. So H is submanifold, so therefore we can find some chart such that its restriction to H is a slice by subspace of less dimension in Kn, right? What I mean by that is that I have phi of U intersect H is this, so x1 and so on, xn in Kn, such that first K coordinates are 0 intersect phi of U. Right, so this phi is exactly from the definition of our definition of submanifold from the first lecture, meaning that its restriction to H is exactly the slice, right, by k-dimensional subspace, by n minus k-dimensional subspace, which is given by putting first k coordinates to 0. So we can find it. So in this case, H is n minus k dimension, right? So since H is given by putting first k coordinates to 0, it is natural, and we would like to consider map on G quotient by H. So we'd like to consider now something where last k minus n coordinates are 0 and first k coordinates, they are arbitrary, right? So let us consider S1 to be the following set. It is G from U such that phi of G is of the following form: x1 dot 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 xk and then zeros. We will need the following proposition. There exists some open subspace of S1 open, and open subspace U tilde of U, of G, right? Such that so this, I put tilde here just to distinguish with this U, such that the multiplication map M restricted to S times H to U tilde is diffeomorphism. Okay, so we're going to prove this in a minute, but and the proof is a bit technical, but just to be motivated, why we are going to fight for such fact. Let us first see how, from this proposition, we can define actually the smooth structure on G over H. So question first, before proving this, question is how proposition helps in constructing smooth structure on G quotient by H. So idea is the following. Well, so we have the following actually commutative diagram. You have S times H, right? And you have M, which is diffeomorphism to U tilde. And then you take P, which is quotient, and well, well, this is just P1. So this is not the P that we used, which is quotient from G to G over H, right? This is just projection to the first coordinate. And then here I take P. So P is our projection, which takes G and gives me the class of G, right? And it maps somewhere to P of U tilde. This is open. This open set in G quotient by H, and we have some map that actually makes this thing commutative, M tilde. So the thing is that if right, so we have these are projections, right? And M sends the fiber of this map to the fiber of this map, and M is diffeomorphism, which defines homomorphism M tilde for us. So M sends fiber to fiber. This is just how, according to constructions of these projections and how multiplication works, fiber to fiber. On one hand, therefore it defines in a unique way homomorphism M tilde. So M defines M in unique way homomorphism M tilde. And this homomorphism will be exactly the chart on G quotient by H around the class of identity, right? So we make the following construction. So around any point X, which is some class GH in G quotient by H, we have open neighborhood. So I take U tilde shifted by G, this G, and consider the projection to G over H, right? This will be open neighborhood around X, which is homeomorphic to open subset of K K by the following map. So this map is M tilde, right? If G is 1, right? Otherwise, we construct this map as follows, as following. So rather M tilde inverse. So by the map P of GU tilde, I need to map it to KK. How? First, I consider left multiplication by G inverse. And left multiplication can be on G or on G quotient by H as well, which maps this to P of U tilde. But then I map this by, so this is homeo. I can take inverse of it and get to S. And then S is mapped. On S we already have chart. Right, I take an element S in here. This is an element in G, right? And it has first K coordinates, right? So S is, so we consider first K coordinates, x1 of S, and so on, xk of S. So this is the map. This is our chart around any point. So the question is why transition maps are smooth, because we would really like a smooth map. So why transition maps are smooth? Why transition maps are smooth? Well, suppose that I have some element in the intersection of two charts, that is P is inside P of G1 U tilde and inside G2 of U tilde for some elements G1 and G2 in our group G. Then what? Then I can write down X as G1 S1 H1, right? Because U tilde is by taking inverse, right? I can go by taking M inverse, right? I can go from U tilde to here. So for any element in U tilde, which is this one, S1, H1, well, X is G1 times some element of U tilde. For any element of U tilde, I have unique pair of S1 and H1. S1 lives in here, H1 lives in here, such that their product is the element of U tilde that I started with, right? And in a similar fashion, I can write it as G2, S2, H2. So actually, X is an intersection, right? This lives in G quotient by H, right? And yes. And so this lives in S, this lives in H, right? This lives in S, this lives in H. And we need the following. We need that coordinates. So what does it mean that transition maps are smooth? We need coordinates of S1 depend smoothly on coordinates of S2. Depend smoothly or on coordinates of S2. So, by the way, this is inside G over H, right? So therefore, this is a class, and the corresponding representative I can write down as this. Therefore, how can I check that coordinates of S1 depend smoothly on coordinates of S2? Well, but smoothly, so we change only coordinates of S2, right? And G1, G2, H2 are fixed. So with G1, G2, and H, 2 fixed. And by the way, coordinates of H1 somehow depend on coordinates of S2. Right, so we have S1, H1 is G1 inverse G2, S2, H2, right? And then let me take coordinates of X1, well, coordinates of X2, X1, first k of them, because the last are zeros. So then out of them I make S2, which is phi of X1, xk, then zeros. Then out of that I make G1 inverse G2, S2, H2. Then I apply M2, M tilde inverse, right? So this guy belongs to U tilde, right? So the whole thing belongs to U tilde, and then I can apply M tilde inverse. All right, then I get S1 H1, right? And then after that I get coordinates of S1, so X1 of S1. So let me continue. So we have a chain of smooth maps. That's what I'm trying to do here. Technically, that's idea is this, and then after that, right? So then I project to S1, and then I go to coordinates of S1, x1 of S1, x2 of S1, and so on, xk of S1. We need, what we need is that numbers that we get here depend smoothly on numbers that we started. And indeed, it is so because all arrows here are smooth maps, just by the construction, but by all the constructions. And yeah, by the way, here it's not tilde. Sorry, this is just m, right? Because just m. And in proposition, we have that m is differ, so it's really smooth. M tilde was homeo, but m is smooth. So therefore, this step is also smooth, and everything works. So transition maps are smooth. We have homeo to open sets around each point, so we have a smooth structure. All right, so now we should fight and for this proposition. So let me restore it. Proposition. I think I just erased it. So we have, so there exists some S inside S1 and E tilde in G, open here, such that multiplication map, such that S times H by M to U tilde is differ. Okay, proof. So we have first observation that I need is that we have the following. If I take differential of this m at identity, so actually at identity times identity, right? And well, so I already have coordinates in here, right? On H I have coordinates everything from k plus 1 to xn. On S I have coordinates from x1 to xk, right? On U tilde I have coordinates everything from x1 to xn. So I have tangent space at E times E here and at E here, and I claim that tangent vector corresponding to coordinate xi by dm is just d over dxi tangent vector to identity in here, right? Indeed, this is just easy. This is almost a tautology because, well, you take your chart, right, and apply phi inverse to the following coordinates: 0, 0, 0, and then you have on ith place xi, then again zeros. And so you take pair this element of a group and identity, right? And then multiply. Here, this is for I from 1 to k. So first let us, okay, this happens for any I, so for any I from 1 to n, right? So let us take, so first let us take I to be less or equal than k, right? This means that the corresponding coordinate in here is in the first factor. So therefore, I take phi inverse of this in the first factor. So here, number of the zeros, including x, is k. The length of this sequence is n, but xi is on the place which is on ith place, which is less than k, right? But phi inverse then will be in s, right? So this is in the first component, and then I take multiplication of this. Multiplication of this with e is actually the same as phi inverse of 0, 0, xi, 0, 0, right? And so what I have, this is, if xi runs over all real numbers, right? This is some curve in where? So this is some curve, gamma of xi, so let's call it gamma 1 of xi, inside s times h, s times h, right? So this is a pair. On the other hand, this is another curve, and its tangent vector is this one, d over dxi, of this curve, a tangent vector to this space. But this is another curve, gamma 2 of xi inside u tilde, right? And tangent vector at 0 to this is exactly d over dxi is a coordinate in here, right? And I take m of it, right? And m takes me one curve to another. So therefore differential takes the corresponding tangent vector to the corresponding tangent vector. So this is really some formula which is tautological, but it explains this tautological formula if you wish, right? So another thing that I should write is that gamma 1 prime of 0 is d over dxi, right? Which is, and we look at this as a tangent vector at e times e at s of s times h, and gamma 2 prime at 0 is d over dxi as tangent vector at e of u tilde. And so m maps this curve to this curve, so therefore differential maps d over dxi to d over dxi. On the other hand, this is for I from 1 to k, because I put this phi inverse into first entry and e to the second. If I is greater than k, then the reasoning is the same. I just need to put this e here and phi inverse of 0, 0, 0 xi 0, 0, 0 into here. And then the argument is the same. And then we get this formula. So what we have is that actually dm, so dm is just identity map if we identify tangent spaces in a reasonable way. So dm, what is important, is invertible. Therefore, we can use inverse function theorem and say that actually M is locally inversible, right? Differential is inversible, therefore M is locally inversible. Which locally means that there exists some S2 in S1 and some V in H, right? Such that, well, and U1 in G, such that Sm restricted to S2 times V to U1 is diffeomorphism. Okay, we're moving towards our statement. You see, here I have the whole H, but here is just some open subspace in H. So this statement is stronger than I have here. So we need to buy the whole H here by the price of shrinking S2 a little bit. So this is the idea. So we can take S from S2, open subspace, so you shrink it a little bit, such that, so it's small enough such that S inverse does not intersect, so intersection with H is inside V. So you can take S such that this is small enough, such that this intersection with H is small enough that is inside V, which is in H. So this is because of continuity of multiplication and of taking multiplication and taking inverse. You can make S smaller so that this is small enough. Okay. But then let me take U tilde, so already U tilde, which is in here, to be actually image under multiplication of S times V. Then M from S times H to U tilde is bijection. Okay, let's see why. So, and this is indeed already what we need. So if we prove that it's bijection, then we are done, right? Because then it's a bijection, and at each point, differential is inversible. So it's really diffeomorphism then. So why it is a bijection? So actually, I think I have some mistake here. I would like not V, of course, here, but H. Right? Yeah, so this is bijection to its image, basically. All right. So indeed, suppose it's not bijection, then we have S1 H1 equals to S2 H2, right? S1 S2 is in S, H1 H2 is in H, and then we have S2 inverse S1 is H2 H1 inverse. So let me define this as H, right? So this is inside what? So H is then is inside S inverse because of that, intersect H because of that. So, but we chose S such that this is inside V, so therefore this is inside V. So H is inside V. And on the other hand, we have S1 times E equals to S2. This is just E identity in G, right? Equals to S2. It's just the games with these identities, not this. S2 times H2 H1 inverse. Right? So we have this is in S, this is in V, this is in S, right? This is in V. And I know that this thing is differ, right? So it's differ to its image. Right? So therefore, and U1 is inside, right? So anyway, so it's if I have two things coincide, right? And it is in these are two things in here, they coincide. M is differ on this set. So therefore, separately, S1 should coincide with S2 because it's differ on a direct product. And H2, H1 inverse should be identity. So, since, so by double star, and double star is this fact here, that this is differ. S1 equals to S2, and H2 H1 inverse is identity, meaning that H2 equals H1. So we proved that if this happens, then S1 equals to S2, H1 equals to H2. So therefore multiplication there is bijection. So therefore multiplication from this to the image of this is bijection. And we are done. So we actually proved the proposition. So it's bijection, differential invertible. So therefore it's differ. Okay. So what did we earn? So we proved that. So we actually defined smooth structure on G quotient by H, and moreover, this we have more than just smooth structure. We have so the corresponding quotient is what is called fiber bundle. So let us see. So let us actually see the definition. So definition. Let X, Y, and Z be smooth manifolds. And suppose that we have the following picture. We have map P from X to Y, and it is surjective, right? It is smooth surjective map. Then P is called fiber bundle. So actually fiber bundle is X together with all this data. P, projection, right? And Z is about to appear. So it's called fiber bundle. With fiber Z. So this is where Z appears. If the following happens, for every point y in Y, there exists a neighborhood U, open neighborhood of this point, so open, and Y is inside. Such that pre-image of U, which lives in X, is actually pre-image is diffeomorphic to U times Z, so fiber is Z, right? So the picture is like that. So you have some U, right, which lives inside Y, and you have X, which is project to Y by P. And at the top of U, each fiber, so to say, is Z, and moreover, the preimage, the whole preimage, is U times Z. So U times Z. So this is Z. So this is the picture. Right. And moreover, I would like, if I would like to have, so if this is some diffeomorphism psi, then psi composed with P, right? It maps from U times Z to U. It's a projection, it's exactly a projection to first component. So this is definition, this is picture. So, and you see, this is exactly what's going on in our case. So around each point, right, we actually have this neighborhood, G, if I have representative, so okay, let me write something, this will be easier to understand. From what we see in the proof, that P from G to G over H, so G over H is now manifold, but so this map is this one, right? But moreover, this is fiber bundle with fiber H. So G is a fiber bundle over the quotient space with fiber H. Because, well, again, around if I fix some G, right, in here, I have right. So I have GU tilde P GU tilde is an open neighborhood of this point, right? Which is like in this definition. This U is U is here. It's P of GU tilde, where U tilde is this from thing from the proposition, right? This map M S times H to U tilde is the bijection. Moreover, it's more importantly, it's diffeomorphism. So diffeom. That's what we just proved. And pre-image, right, of this thing is diffeomorphic to actually S times H. So this psi here right, so the pre-image of this, so I need to so this psi is actually what? So pre-image of P of GU tilde is GU tilde times H, right? So this is G U tilde times H, right? Then I apply left multiplication from the left on G inverse. I get U H U tilde H. All right, and then so I would like to apply M inverse, right, to get S times H. What I don't like here is this, right? Well, okay, so this anyway, so our fiber bundle is the following. So we have so this is fiber bundle with fiber H. Why? Because this is our U in here, right? And this is actually diffeomorphic by taking M inverse and left translation by G inverse to S times H. So like in this. And we're using that M is S times H to U tilde is diffeo, right? So therefore, if I multiply by H here, right, this means that I just multiply by, so U tilde times H, right, is the same as U tilde times H is the same as U tilde actually, right? Because U tilde is obtained by multiplication, something from S times something from H. And so as we run everything from H, we just go over all elements in here, right? And so our psi is first I apply this, and then I apply M inverse. And then I get to S times H. Right. Okay. So this is fiber bundle, and this is very good because then, after suffering for so much, we can get a lot of good conclusions out of this fact. In particular, suppose that we have lemma. Suppose that we have the following. So lemma. Suppose that I have P. It's a map from manifold X to manifold Y, and it's a surjective. So surjective map, smooth. Such that, well, in coordinates, in some coordinates, it looks as just projection to first, say, K coordinates. Well, more concretely, it means that, so for every X in X, there exists a chart phi X, and if I take Y to be P of X, there exists chart phi of X, which goes from some neighborhood Ux containing X to Kn, and chart phi Y. It's from chart in Y, containing Y, to K M. So here M is dimension of Y, N is dimension of X. And in these coordinates, our P looks like this. So if I precompose P with phi X inverse and then phi Y, then it just takes x1 xm, then xm plus 1 xn, and then it just forgets about n minus m last coordinate. So it's just x1 xn. So suppose I have surjection smooth map such that around each point we have fine coordinates such that this map in this coordinates just forgets about some number of last coordinates. Then for any commutative diagram, So like this, x, y, z. So from x to y I have p, and then I have two maps from y to z and from x to z. This one we will call fx, this one we will call fy. For any triangle like this, we have fx is smooth if and only if fy is smooth. Well, this lemma is actually obvious, nothing to prove here. It's just because you see, so f of x from x to z, it depends on n coordinates, around each point. Choose this coordinates which work like this for the map p. And since f factors through p and f, right, it should not depend on the rest of the coordinates because f does not depend on it, right? And so if fy is continuous, it's smooth, it is smooth in this first coordinates, x1, x10, right? On the other hand, since fx does not depend on the rest of coordinates, so it's also smooth, right? And the other direction, the other direction is also clear, right? Because then f of x is just, since this is smooth, right? Then, and p is smooth, then, the thing is that f in coordinates is just value of fy in coordinates. There's value of f of x, which when we just forget about this last coordinates, right? And so for both, checking smoothness for both maps is just checking smoothness, smooth dependence on the first m coordinates. That is how you just prove it, but it's more or less obvious. And the thing is that fiber bundle, satisfies the lemma. So you just, again, you just need to, remember the definition of fiber bundle, and then your, you can choose an atlas, which is in this trivializing neighborhood, right? Choose choose coordinates in this atlas, in y, right? And then choose coordinates on z, on the fiber, right? And then this projection will be exactly forgetting coordinates on the fiber. So fiber bundle satisfies the lemma. And we actually can now get a lot of things, not for free because we worked hard to get this, but immediately after we know what we have. For example, we can prove now the following proposition. What we started with. We wanted the action of G on G quotient by H to be smooth, right? And indeed, so the action, this proposition says that the action of G on the quotient, so how it works, G acts, again, just to recall, this pair is sent to this class. So the action is smooth. So we just need to apply this lemma. So proof is this. We take G times G. Let's draw some commutative diagrams. We can apply multiplication map and get to G. We can, from G, we can by P get to the quotient, G quotient by H. Then we can, from here, by identity times quotient, we can get to G times the quotient. And from here to here, we can get by alpha, which is this map. And this diagram is commutative, of course. All maps, so we would like to, so all these maps, M, P, identity times P, are smooth. And we are trying to prove that alpha is smooth. So we also need this diagonal. This diagonal is smooth, and this is also fiber bundle, by the way, right? And this is fiber bundle. So both these triangles, they satisfy this lemma, but we actually need this one. So this triangle is this one. We apply, and this triangle will go to this one. Now, this diagonal is smooth because it's a composition of two smooth maps. So this is smooth. This is fiber bundle. So therefore, this one is smooth and this one is smooth simultaneously. So therefore, alpha is smooth. Right? So M, P is smooth. So M, first I go by M, then by P. So M, P is smooth as a composition of smooth maps. So therefore, alpha is smooth. By the way, here it's the other way around, right? So therefore, alpha is smooth. This is by lemma, by applying lemma to the map ID times P, which is also fiber bundle. Okay, and maybe the last statement for this lecture. Suppose that we have proposition. So we proved this proposition. So we reached our goal. Okay, we introduced smooth structure on G over H, and we proved that this smooth structure is such that this alpha is smooth. And this is because we have good smooth structure in the sense that corresponding projection is a fiber bundle. So this is a quick review of what we have done. But let us also prove the following proposition. So suppose, so let H inside G be a normal Li subgroup. Be a normal Li subgroup. Then G quotient by H, of course we know from the group theory that it is a group, but the statement here is that it is actually Li group. Okay, how to see this? So we just need to prove that multiplication. So we have smooth structure here, and so with respect to this smooth structure that we introduced, multiplication and taking inverse is smooth, right? So we have again commutative diagram. G times G by M goes to G. Then we have projection here. Then we have projection times projection here. And then here we have what is multiplication in G. So M tilde is multiplication in G quotient by H. And we just follow the same logic of the proof of the previous proposition. So we have this diagonal. It is M and then apply P. It is smooth, right? So this is already proof. Right? This is, so again, M composed with P is smooth. Therefore, M tilde is smooth. And this is again apply Lemma, the previous Lemma before these propositions, to fiber bundle P times P. And this says that multiplication on G over H is smooth, and the smoothness of taking inverse in G over H, right? Which is, I take class of G and have send it to class of G inverse. Smoothness of this is just proved in a similar way. Just again, you'll have this square, diagonal, and then apply Lemma, right? And you'll get the smoothness of this I tilde. Okay, so I think this is a good place to stop this lecture.